All right. So we want to represent a circuit without knowing what's inside. And ultimately with this, this just tells the designer how they can integrate a component. So for instance, it might tell them what the input and output impedances are. And whether the circuit has some gain or loss. And they don't need to know anything else about the circuit beyond that in order to incorporate it in whatever they're doing. So this concept of two-port networks, ultimately, we have this generic network. It has two ports at the input, one at the input, one at the output. And sometimes they call this generic network a black box. We don't know what's inside. There's some magic going on. We don't need to know what's inside. We just need to know how it interacts with the real world. All right. So for us, for the time being, we're going to be talking about passive, or I should say, we're going to be talking about small signal S parameters or small signal network parameters, and that means that we're going to have a couple of important properties. We're going to have a property called passivity. And this just means that there are no internal power sources. There are large signal network parameters that do have large signal, that can have internal power sources inside of them. But for the time being, we're talking strictly about passive networks. And we're also talking about, we're going to consider that these networks are linear. Ultimately what we mean here is that, any voltage or current is a linear function of the input or output. Okay. These are generally true for networks with no active circuits. And what we're going to, what we mean by an active circuit is generally a circuit that has a transistor in it, although there are other nonlinear circuits that don't have transistors like diodes, but generally we're talking about transistors. And if we do have an amplifier, the network is considered to be linear in the sense that if we have a parameter related to gain, we assume that the gain is linear across all possible input powers. That is not how real circuits behave, so we're considering these as small signal. We put a small signal in, we get a small signal out. Now, how do we tell if we have a circuit that's a small signal circuit? If we put a signal in and say the circuit has some gain associated with it, then we expect that what we get out is just a linearly scaled version of what we put in. If there's any distortion or reshaping. So for instance, we put a sine wave in. If there's distortion or reshaping of the sine wave, so for instance, we start to flatten or compress the sine wave, that implies that there's some nonlinearity or something going on other than a linear operation. Okay, now you might have in prior classes seen other types of network parameters that can represent a black box. If you've taken my analog circuits course, you've certainly seen some of these. We know that there are things called Z parameters. This is where we're representing the two-port network or the black box in terms of voltages and voltage and current ratios. So the voltage to current ratio at the input, the output, across the input to the output. We have Y parameters. This is just the inverse of a Z parameter. We have hybrid parameters like G and H parameters. We have a set of parameters called ABCD parameters that we use in microwave circuits. And all of these different network parameters are really just telling us something about the relationships that happen at the ports of the circuit and across the ports of the circuit. Okay. Now we have a problem when we start going to high frequency. So let's take a look at what that is. So these are Z parameters. And the Z parameters are really just an expression of a set of linear equations relating voltage to current. So for instance, we have V1 is equal to Z11 times I1 plus Z12 times I2. And V2 is equal to Z21 times I1 plus Z22 times I2. So we can write this in matrix form. And essentially, we have a response matrix V consisting of voltages, a stimulus matrix consisting of currents, and our network matrix that tells us how the voltages and currents relate to one another. If we want to find any one of these parameters, so for instance, Z11, if we want to find Z11, we know that we need to eliminate Z12 somehow. Well, we can't eliminate Z12, it's intrinsic to the network. But what we can do is eliminate the stimulus that would trigger a response from Z12. So for instance, if we were to solve this upper part of this equation, we would find that the Z11 is equal to V1 over I1 if we make I2 equal to 0. And we can ultimately any of these network parameters, it's Zij. I is the output, J is the input. So Z12 is V1 over I2 when I1 is equal to 0. And we can quickly write the other ones just following that rule. All right, so what's the problem with this when we go to high frequency? It'd be nice to be able to use these things at high frequency.
There is no scattering stuff,
reflection. Well, we'll get to scattering in a minute, but just think more fundamentally. If we go to high frequency and we try and measure this, it tells us that we need to put a perfect open circuit at the output of the circuit.
It's not possible because of the parasitic.
Yeah, and at high frequency, we have parasitics, right? So I try and put an open circuit at the output of the network. That just means I should leave this dangling, right? Ideally, you know, I just leave this dangling. But in reality, if I put any type of probe anywhere near it or just a physical manifestation of the circuit itself, it's going to have some parasitic capacitance and probably some parasitic resistance. So I try and put an open circuit at the output, and I can't do that. All right, now just to close the loop here, what do Z11 and Z22 mean physically? It's more or less the input and output impedance of the circuit. And what are Z21 and Z12? Yeah, these would be called transimpedances. So it's not necessarily a gain. It's the ratio of the output voltage to an input current. Okay, now, well, we couldn't make an open circuit. Let's see what happens if we want to use Y parameters instead. Our Y network is just the inverse of the Z network. So we can say I1 and I2 are our outputs. Our network parameters are a set of Y11, Y12, Y21, and Y22. And our inputs are V1 and V2. And much like before, we're going to go through and try and eliminate one of the stimulus ports in order to solve for this. So Y11 is I1 over V1 when V2 is equal to 0. And we can go through and quickly write all of these. All right, well, can we make a perfect short circuit? Yeah, most likely I try and make instead of trying to make a short circuit, I'm going to get something like a lossy inductor. All right, so that motivates the need to come up with something else in order to do our analysis. So we want to be able to measure it. Now, when we're doing on paper circuit analysis, I can make a perfect short circuit and I can make a perfect open circuit. This all comes down to when I actually want to measure something at high frequency, what do I do? All right, so we talked a bit about the reflection coefficient in the past. The reflection coefficient is what it sounds like. We have a wave propagating into our system, or they call it incident upon our system, and it hits our system, and some of the wave is returned or reflected out of the system. And the reflection coefficient is a ratio of what is reflected out of the system, denoted by V minus X, to what is incident upon the system, denoted by V plus X. Okay, so we come into our circuit here and we put a load, ZL. And exactly at this point, we'll call this distance 0 in the circuit. We can tell what the reflection coefficient is at that point. And this is what we defined earlier. The reflection coefficient is the ratio of the load impedance minus the characteristic impedance of the system over the load impedance plus the characteristic impedance of the system. And we can work in admittances if we want to. The same holds true if we work in admittances. We just need to note that Z naught is equal to 1 over Y naught. ZL is equal to 1 over YL. And we can plug things back in. And it's also true if we work in currents or in voltages. So we can work in currents or in voltages in any of these systems. All right, so here in our system, we have a wave that propagates in V1 plus, and we have outputs that might propagate out of the system, V1 minus and V2 minus. If we put an input in instead at port 2, then we can have we have an incident wave V2 plus, and coming out of the circuit could be V1 minus or V2 minus. And so we can write another system of linear equations. You can say that V1 minus is equal to S11 times V1 plus S12 times V2 plus. Oops. And V2 minus is equal to S21 times V1 plus S22 times V2 plus. It's very similar to the form that our parameters took before. I should note that you can do a transformation from any set of network parameters to any other set of network parameters. So for instance, you can easily transform Z to Y, Z to ABCD, Z to S, S to ABCD. They all have relations to one another. You just sometimes need to know what the characteristic impedance of your system is, or some secondary clue. But you can find all of them from if you just have one of them. Okay, now much like before, if we want to find S11, we need to eliminate one of the stimulus or stimuli. So S11 is equal to V1 minus over V1 plus when V2 plus is equal to 0. And S22 is equal to V2 minus over V2 plus when V1 plus is equal to 0. Now, if I look at that, that looks an awful lot like a reflection coefficient, right? I have a reflected signal over the ratio of a reflected signal over an incident signal. And indeed, these do relate to the reflection coefficient, or ultimately to the impedance. They're not exactly equal to the reflection coefficient. And the reason is that I can have a signal that propagates through the block, hits off of the load, reflects off of the load, and comes back through the circuit. So in that particular case, they would not be, it would not be equal to the reflection coefficient purely at the input, because I'd be getting signal back from all the way from the load. But they're related. If I have if I have a perfectly matched load so that I don't get any reflection off of the load, then it's equal to the reflection coefficient. All right, I have S12 and S21. S12 is equal to V1 minus over V2 plus when V1 plus is equal to 0, and S21 is V2 minus over V1 plus when V2 is equal to, V2 plus is equal to 0. And what are these? What are these things? Or transmission. So transmission through the circuit. All right, and I'm going to say again, related to transmission. And the reason to say related to transmission is if I don't have a perfect input match or a perfect output match, the signal is going to, some of the signal is going to get reflected off of the input. I don't know what portion, or I have to do some calculations to figure out what portion got reflected versus what portion got sent through after the reflection. But they are related to reflection. Okay, now why are these things interesting to us? Because I'm looking purely at a ratio of voltages. I don't need to have a perfectly matched impedance at the input or the output to find that ratio. I don't need to have a perfectly open circuit or a perfect short circuit. And I can still find the ratios. So that's why we choose to work with S parameters. Any questions at this point? Okay. All right, you can always feel free to stop me at any time. All right, so we can find, as I mentioned just a moment ago, we can find any network parameter from any other network parameter. So if I have S parameters, I can find Z parameters from the S parameters. So for instance, Z11 is equal to 1 plus S11 times 1 minus S22 plus S12 times S21 divided by the determinant of the S parameter matrix. Z12 is given here as well. Oftentimes, I normalize my S parameters. So for instance, I like to deal with normalize, or I normalize my impedance parameters as well. I like to deal in impedances that are normalized to a fixed impedance. What do I normally, or what I usually normalize to? Yeah, almost always 50 ohms. Why? Why is 50 ohms popular?
People like 50.
Almost true. What you know? What your cable TV? You all still have cable TV, at least for internet, mostly, right? What is the impedance of the coax that's going into your cable? It's 75 ohms. So it turned out when they were making coax cables back in the day, around 100 years ago, they could only extrude things, plastics and whatnot with certain shapes and geometries. They don't have the advanced manufacturing that we have nowadays. And so with the materials and the way that they were able to shape them, they could make a transmission line that had the maximum, I think it was maximum power transfer at 33 ohms and the minimum loss at 75 ohms. And 50 ohms was a good compromise between maximum power transfer and minimum loss in a cable. And so we are stuck with it today because of that. Nowadays we can make a transmission line with any impedance that we want to, practically. But when you get a legacy investment in infrastructure, it takes a long time to get rid of that. So 50 ohms is our choice.
So I have a question here. So
Yeah.
if we have 50 ohm output impedance, then if we let's say have a common source amplifier which requires high gain for high impedance, and how do we connect it?
So we'll look at a common source amplifier. If we look into the gate of a MOSFET, the gate of a MOSFET is always highly reactive. And so we have to synthesize an impedance, a real impedance. We're going to do that with negative feedback, actually. So we'll show you how to do that in a bit. But yeah, we have to synthesize a real impedance. All right, so we can relate S parameters to reflection coefficient, as I mentioned just a moment ago. So our reflection coefficient gamma n is related to what I put into the circuit V1 plus and what comes back out of the circuit. But it depends upon what the load is on the output of the circuit. I define gamma n is equal to V1 minus over V1 plus because that's the only thing that I can observe in the circuit. I know that V2 minus is given by S21 times V1 plus S22 times V2 plus. I know V1 minus is equal to S11 times V1 plus S12 times V2 plus. And I can further find the reflection coefficient at the output if I know the ratio of the incident wave at the output and the reflected wave at the output. And if we put all of these equations together for V2 plus and V2 minus and solve for gamma n, you can show that gamma n is equal to S11 plus S12 times S21 times gamma, L over 1 minus S22 times gamma L. And likewise, we can start from the output port and go back through the circuit the other way. You're going to get a very similar expression. Really, we're just going to swap 2's for 1's everywhere. All right, now what this tells us is that if if the signal, if there's no reflection off of the load, gamma L goes to 0, and then gamma n is equal to S11. Or if either of the transmission parameters is equal to 0, then gamma n is equal to S11. When we make amplifiers, almost any passive circuit that we make is going to be reciprocal, which means that whatever S11 equals, whatever S21 is equal to whatever S21 is equal to S12 is going to be equal to. But active circuits, oftentimes, we want it to amplify in one direction and do nothing in the opposite direction. So when we make amplifiers, oftentimes we're trying to make S21 big and S12 equal to 0. And what we're going to find is that this causes us tons of problems with stability if we aren't able to successfully do that. We can say the same thing for gamma out if gamma S is equal to 0 or the one or the other of the transmission parameters or both is equal to 0, then gamma out is equal to S22. This is really just a condition telling us it doesn't matter what happens at the load or at the source. All right, any questions? So where we're going with this is that we have the ability in all of our RF simulators to do something called an S parameter simulation. The S parameter simulation is going to be able to tell us or at least relate to input and output impedances and gains. Okay, we like to talk about things in terms of what their impact is to the circuit. Ultimately, why am I doing all this? I'm going to be making some analog signal processing circuits like gain blocks and whatnot. I'd like to know if I put something in, how much do I get out on the other side? You know, how much is reflected off of the input? And I like to quantify this generally in terms of dBs because I like to, I'm good at adding, I'm not good at multiplying. Right. That's ultimately why we use dBs, right? Okay. So what we just mentioned is input reflection coefficient is equal to S11 if the load has no reflection or if the transmission is 0 in at least one direction. And we like to talk about a parameter called return loss. And return loss is just a ratio of how much power is reflected from a port due to what's incident on the port. And because it's a loss, I take the inverse of that ratio. So for instance, here, return loss is equal to 10 log 10 of power incident on the port over power reflected from the port. We can write return loss as a function of the reflection coefficient. It's just minus 20 log 10 of gamma n. And we can do this at the input or the output. So if the load impedance is more or less equal to the complex conjugate of the characteristic impedance, then we can say return loss is approximately 20 log 10 of S11 at the input, approximately minus 20 log 10 of S22 at the output. Typically, we consider an impedance match to be good if the reflection coefficient is less than minus 10 dBs. Or sorry, if the return loss is less than minus 10 dBs. This corresponds to something like 0.316 in the linear domain. Or 2-to-1 Viswar for Peter.
Question.
Yeah.
Why is it approximate?
Well, I guess I should say if it's not approximate if that condition is met. But sometimes we don't quite meet that condition, it's close enough. So if C, let's just say, how about this? We're gonna make this approximate and that approximate.
Excuse me, what's the use of the SP? What's the SP?
S parameters. Okay. Now, this return loss is really just telling us like how good the match is, but it doesn't tell us how much power is actually lost due to a mismatch. So we have another quantity that we can use called mismatch loss, and mismatch loss is defined as 10 log 10 of the power at the input over the power at the input minus the power that's reflected. And we can have mismatch loss at the input or the output. And what this is telling us is I put a signal in, some of that signal gets reflected, never goes into the circuit. This tells me how much never got into the circuit, how much power was just purely bounced off of the input. Same thing at the output. How much, if I send a signal out to the output, how much power gets bounced off and never shows up in the load. Now, ultimately, what this is getting at is S21 we said related to transmission through the circuit, but it's not exactly equal to transmission through the circuit. And so we also have the concept of insertion loss, and insertion loss is telling us, how much power that's delivered into the circuit is actually lost in the circuit or in the device under test, in that black box. And insertion loss is equal to S21 in dBs minus the mismatch loss at the input in dBs minus the mismatch loss at the output in dBs.
Does it also include amplification? Does it match?
Yes, so we talk about insertion loss in terms of, so far we're talking about passive networks, but the same holds true if we were looking at an active network that had, say, some power gain. Now, we're still talking about things in terms of small signal linear approximations still. Okay, now we can have networks that also have more than 2 ports. We will use them fairly commonly. So for instance, couplers have 4 ports. Diplexers are filters that might split the signal and filter it with different frequency responses in 2 different directions. Those have 3 ports generally. We have isolators that sometimes have 3 ports. So we can have definitely more than 2 ports. If that's the case, we just expand our interaction matrix like so. You'll notice a couple of things about the network. Each row more or less tells me what the response is from the row number to every other row, or to every other port. And each, the diagonal will always have more or less what the reflection coefficient is going into any one port. That's assuming all the other ports are matched. Okay, there are special networks that we like to talk about from time to time. So some of our networks are symmetric. If you, for instance, have a resistive circuit that looks like this. I have R1 in series and R2 shunted to either side. It stands to reason that this circuit behaves the same way, going whether I connect the circuit as input at port 1 or at port 2. So this is a symmetric circuit. If it's a symmetric circuit, we can generally say S11 is equal to S22, and S12 is equal to S21. What types of circuits do I make with resistors like that? Resistive ladders. Attenuators. I heard attenuator. Yeah. Yeah. Normally we make attenuators. We can make other things, but generally attenuators look like a pi-based resistive network. We can also have reciprocal networks. These are similar. The output at port X due to an input at port Y is the same as the output at port Y due to an input at port X. All networks that are symmetric are reciprocal, but it's not necessarily the other way around. All right. Everybody comfortable with S parameters? All right, let me see if I can pull up a few things here before we move on to noise. I do apologize for our clusters. We're working to replace them. Sometimes this will connect and sometimes it won't. All right, well, it's gonna.
Yeah, this is a realistic simulation of what it's like to work on RFICs at the Tech.
Well, I have a workaround, but I'm trying to find a way to do it for class. MOBA X term.
All VLSI and analog IC students had a very similar experience at certain times of the semester last year.
I'm aware. I've been trying to fix it for a while now. But I am only one person, and I am a professor, which means I'm the lowest person on the totem pole. You have the possibility, and many of you already are, alum. And alums sometimes come back and write giant checks if they have positive experiences at the university. So you have a lot more power than I do. All right. Now I know what's going to have happened to me. Is I'm going to have been locked out of Duo because PT-Arc is doing this thing where I have to call.
So, Professor, are you able to use like the ARC server now? You've done like.
I have VT-Arc set up for some very specific usages. It's not. We aren't able to have the class use VT-Arc, so we're working on a few other solutions. We will have something better than what happened for analog last semester, I promise. But I have been locked out of Duo. Okay, well, it's fun. I get to call later tonight. All right, well, that's not going to work. So I'm not going to be able to show you S parameters. I will do so on Wednesday. But let's show you. All right, you're going to have to do a homework problem where you actually use do a hand Smith chart. Oh, I need to. I'll upload a Smith chart if you haven't found one on the web, but generally you can just find them on the web, paper charts. I end up always using this online Smith chart tool. It's pretty nice. It's by this chap named Will Kelsey, and it's pretty cool. You put your frequency in. Five gigahertz, give it a characteristic impedance, and then you can set some objectives like, for instance, I want to, I don't know, start at 10 ohms, and I want to match to 50. So if I want to match to 50, I can go, I need to go in this direction, so I can either use a series inductor or series cap. So the cap is going to move down on a line of constant conductance, sorry. Oops. Bigger series cap. And if I wanted to go to 50, now I need a shunt component. And I'm moving up. Inductors always move up, capacitors always move down. So we can grab a shunt inductor. Needs to be a little bit bigger. Sorry, a little bit smaller. Here we go. Matching network done. This is why we like to use Smith charts. I could have hand calculated that. We did an L match the other day. L match, even when you're good at hand calculating them, takes a few minutes. You can of course write a MATLAB routine that'll do it for you if you want to. On Wednesday, I'll set up an S parameter simulation. I do have a demonstration of doing an S parameter simulation in Cadence online and using the normal flow.
Question?
Yeah.
How could you estimate? Is there a way to quickly estimate the Q of this network in the Smith chart?
So in this particular case, the Q of the network, if I assuming that there's no quality factor for any purely real impedance, the quality factor is equal to 0 for any purely real impedance, I'll assume that I got close enough to a real impedance here. The quality factor is just the ratio of the reactance to the resistance. If I do this with more than 2 elements, so let's say that I shot past 50 and so I shot past 50. Now I need to go up a little bit higher, and now I need to come back down on a line of constant conductance. I'm going to add a capacitor here.
Is it needed to use for a tolerance to have a good match or find the quality factor?
So, are you talking about the tolerance number?
Yeah.
The tolerance just adds uncertainty because when I make a real circuit, so I could probably actually find every one of these components in a kit of inductors and capacitors. I know I can find 1.2 picofarad. It's a standard value. 0.8, I don't remember. Sometimes you can find 0.8, sometimes you can't. 0.75, I think I can generally find. These are all going to have these are all going to have tolerances when I buy them. most of the time, if I'm buying cheap parts, they're going to have 5% tolerances. And so when I add all of those tolerances, this just shows me the range of possible values that I might have after the tolerances are added to the circuit. There is no such thing as getting a perfect impedance match every single time. Every circuit that you build is probably going to have plus or minus 5%. Maybe on an integrated circuit, you might get a little bit better than that if you make a big enough component, but it's probably also going to be pretty close to 5%. So normally when I make a spec for a circuit, the spec will say that the return loss has to be better than, nobody ever says minus 10 dBs because you want it to work over PVT variation, so they'll say minus 15 or something like that. If you have a really mean manager, they'll tell you minus 20. And I think on here you can also put, you could put you can put circles that that relate to reflection coefficient. I thought, I don't remember how to do that. I could put a circle around here that told me what the circle was for minus 10 dBs return loss, and what I'm going to try and do with all the tolerances is make my design so that everything lands inside of that circle. Some networks will be less sensitive to component variation than others, so things to think about. Okay. The key that I was getting at if I want to know what the Q of this network is, I find the sum of all of the non-real nodes in the circuit. So I find the Q here and the Q here, and that would tell me, and I add them together, and that would be the total Q of the circuit. Yeah.
Does it always add up like Q1 plus Q2 plus?
It comes pretty close to that. Yeah. It's not. There's always a little bit of a variation, but it's pretty close to that. Yeah.
What if you're like end up say you didn't need to match to 50, you need to match to 50 plus 10J, like so now that's a reactive.
That node has some reactance. So basically you just find all the reactive nodes in your circuit. Yeah.
Wait, once you're at the end, the first one.
Well, the first one is zero.
Yeah.
If I do, okay. The other thing to think about is that this is the network queue. So is it bad if I have a network queue of 0?
You can have a 0 if you want to match it. If you have a match output which is matched exactly, your job would be.
Yeah, imagine that I had a bunch of ideal components, inductors and capacitors, and I wanted to make little infinitesimally small movements. Like, I go down, back up, down, back up, down, back up. I just keep doing that. Infinitesimally small movements. If I do that, I keep a Q of 0 in the network. And that implies that my bandwidth is going to be very wide. It doesn't necessarily imply that my loss is going to be bad, because all of the components are ideal. So there is a difference between network quality factor and component quality factor. I want my component quality factor to be very high, but my network quality factor is what's going to dictate what the bandwidth is. Now, if my components are lossy, then they're going to start coming into play. But ideally, the network queue and the component queue are not related. In practice, they're somewhat related, especially if the queue of the components is low. Okay, any questions on that?
So when you say component queue, you mean like the queue of like the inductor and whatever series?
Right. So an ideal inductor has a component quality factor of infinity.
Right. There's no
There's no loss in it. There's no loss. So it's more or less the ratio of the energy stored to the power lost, right? So there's no power loss, so there's no resistance. So ideal components have infinite quality factors, but the network itself has a quality factor that's independent, well, to a first order independent of the component quality factor, as long as the component quality factor is high. In our circuits that we're looking at, RFICs, almost always the inductor is lossy, the capacitor is relatively less lossy. There are different rules that can change that. So inductor quality factor, we'll look at passives in a few days. Inductors typically have a quality factor between 10 and 20. Capacitors are typically better than 50. There's some frequency dependence to that as well. Okay, any other questions about matching networks? All right. Oh, I should ask also, all right, so we're going to talk about something a little bit different, but still related to two-port networks. Noise. All right. So we know that all electronic circuits or all real circuits have noise in them. And it's generally related to some type of loss or some type of non-ideality in an active circuit. We know, for instance, that if we have this two-port network, we short the inputs and we were to be able to measure the output, you know, over time, we'd still see some small wiggle on the output on the load, and that's due to noise. And the way that we typically model a noisy circuit is we use a noiseless circuit and we extract an equivalent resistance and an equivalent noise voltage, Vn squared. In certain circuits, we might also extract a noisy current source as well. And a shunt resistance to model noise. Okay, so transistors have a couple different types of noise. Yeah, thermal noise, this is, you know, due to what we generally model as Brownian motion in the circuit. They have shot noise, flicker noise, something we call burst noise. And there are a few other types of noise as well we won't talk about. But generally, these have to do with imperfections in the lattice when we make the circuit, or imperfect recombinations of carriers in the circuit, or maybe inopportune recombination of carriers in the circuit. For a resistor, we know that the noise, Vn RMS, is equal to square root of 4 times K times T times B times R, where B is the bandwidth of interest. So, you know, we're generally looking at bandpass circuits. So there's some low frequency and some high frequency that we might be concerned with. T is the temp in Kelvin. K is the Boltzmann's constant. It's 1.38 times 10 to the minus 23. Yeah.
Minus 23.
Oh yeah, minus 23, sorry. That would be a lot of joules per Kelvin. And then the noise power is equal to the RMS voltage squared over 2 times the resistance, which is equal to, sorry, over the resistance, which is equal to KTB. I just moved the 4 over. We have a concept of what we call, and I've written this down incorrectly, noise factor. So in analog circuits, we often do things in terms of input referred noise. So we'll take all the noise in the circuit, we'll refer it back to the input. In RF circuits, we oftentimes just want to know what the degradation is in the noise, in the signal to noise ratio from the input to the output. And noise factor is a way of measuring that. So our noise factor is equal to P n sub 0, which is the noise power at the output, divided by P n sub I minus GA, where this is the noise power at the input, and this is our available gain. All right. And GA we generally write as P times the signal at the output, or sorry, P of the signal at the output divided by P of the signal at the input. Okay, so what F is measuring is how much does the signal to noise ratio degrade from the output or from the input to the output. So we can actually make some substitutions and write F is equal to PSI over PNI, where this is SNR at the input, over PSO over PNO, where this is SNR at the output. All right. Now, unfortunately, every circuit that we make will make the signal to noise ratio worse. There is no way to make it better with any real circuit. So our job when we start to make receivers or amplifiers is to make that signal to noise ratio degradation as minimal as possible. Now, we can cascade noise in systems as well. So for instance, here, let's say I have an amplifier that has some noise and it's cascaded into a second amplifier that also has noise. This is fairly common. We have one amplifier, we can't get enough gain with one amplifier, so we add 2 amplifiers in our system. Let's see what the impact of that is on the noise figure. Well, we can go through just by putting some noise signal at the input. The power of the noise at the input is equal to KTB times R. And we can work our way through and show that the power of the noise at the output is equal to the gain of the first stage times the input noise plus the noise of the transistor times the gain of the second stage plus the noise of the second amplifier. And if we go through and write that the noise factor is equal to PNO over PNI times GA1 times GA2, we can pull a couple of interesting things out from here by making substitutions. The total noise factor is equal to the noise factor of the first stage plus the noise factor of the second stage minus 1 over the gain of the first stage. And if we show the noise factor of the first stage F1, it's just equal to 1 plus P N1 over P Ni times GA1. So this is kind of an interesting result. It tells us that if we cascade multiple stages, that though every stage contributes to the noise factor, the noise of succeeding stages after the first stage is suppressed by whatever gain comes before them. So if I look at F here, the noise that we get from the first stage shows up dB for dB at the output. But the noise that the noise contribution from the second stage is suppressed by the gain of the noise contribution from the first stage. So when we start to make receivers, we're going to try and put a lot of gain at the front, because whatever gain we put at the front is going to start to reduce the contribution of noise from
Hello, Professor.